Okay, then now we can get started. Okay. So which course is killing you? I don't think it's mine, right? It's everyone seems to be doing okay. From what my impression, and I have been quite relaxed about the course and everything. Although what we want to take note lah. So a few announcements before we get started. We are in week 5 already. So our first quiz is next week. Okay, so it's next week, and I think I will probably put the quiz on upload available on Noisy. Hang on. Hang on. Okay, how about now? Can you hear me now? Okay, so yay. Yeah, so I was saying we have our first quiz on next week. So I will make it available online on Wednesday, and then there's 24 hours to submit. So let's do it on Wednesday 12 p.m. to Thursday 12 p.m. Okay, so exactly 24 hours, and then the topics that we will cover is chapter 1, 2, and 3. I will write down and email an announcement so that you can remember lah. Okay, then so that is one thing. So we have our first quiz, and then week 8 will be our midterm test. We will do it on the Wednesday lecture slot, and so let's see how fast we can cover. I aim to finish at least parts of chapter 5 before we start our midterm test, right? So yeah, let's see how far we cover. So it's at least until chapter 4. Chapter 4 is about momentum. It's quite short, and so that one will go through pretty fast, I think. And also one more thing. I'll be announcing talks to you throughout the semester, right? So this one I'm mentioning to you now is my own talk given by me this Friday. So this Friday I will be talking about black holes. Yeah, so I'll be talking about black holes, and in particular about this year's Nobel Prize, right? So I will explain why or what is the work that went into when we talk about the Nobel Prize. Okay, so everyone good? Let's get started now and talk about the potential energy. Okay, so okay, so everyone is still with me, right? My mic I'm still talking, right? It's a bit of a problem nowadays, the microphone. Yes, okay, great. Wait, okay, great. So let's continue with so we're talking about potential energy, right? And we were in the previous class, right? We mentioned until the part where the concept of potential energy is just where if you differentiate the potential energy function, you get the force. So the force is the derivative of the potential energy function. That means if you plot the graph of U against X, then you can actually, from reading the graph, you can actually determine the force because it's the gradient, right? So it's the gradient and it's the slope. So because, right, this is true, then we can determine the qualitative features of the force by reading the graph. So yeah, so we can determine the qualitative features of the force by reading the graph of U against X. Okay, so for example, right, you have a potential energy function that is some function, so you can plot it like a graph, and then you can get a few features about it, because F is du dx, right? So it's the derivative. So if I look at this point, for example, right, so for this position x, okay, so if I look at this point, right, the slope of this graph is downwards, okay, so it's a negative gradient, but negative of du dx, it will give you a positive number, so this will give you a positive force, right? So if I take this is my x-axis, we follow the direction consistently, that means it will experience a force that is acting along towards this direction, okay? So if I take another point, right, so let's say this position, right, and then you calculate the du dx, you get this gradient is a positive gradient, but it's a positive gradient, negative of this number should be negative number, so this particle, if the object is located at this position, it will experience a force in this direction, okay? And then so you have positive force, negative force, and then if you are here, this is the minimum point. Minimum point, of course, is where the gradient is 0. So if the gradient is 0, the force is also 0, okay? So if the force is also 0, this is equilibrium, right? Force is 0 means equilibrium. Okay, so same thing over here, you look at this point, then you get this gradient, so the force will be in this direction, and then this is another point where the slope is 0, okay, so this is another 0 force, so 0 force also means it's a equilibrium as well. Okay, so this is the force, right, in relation to the potential energy graph. Is my mic working? Why there's a negative before dv dx is by definition. Okay, so if you remember the last class, right, we define potential energy to be the negative antiderivative, purposely defined one. Okay, so yeah, so it's purposely defined, because if you define it in the opposite sign, right, then the whole graph is upside down. Okay, but if I define it this way, then if I draw this graph, so I will get this direction. Why do we want to define this way? Okay, so you see why this negative is important. So that it helps us easy to imagine, right? So if I have a particle here, right, it's almost like this one is like a mountain, right? And if I have a particle here, and with the negative sign, the force is pushing here, so that means the particle will try to move to the right. Okay, so it's moving to the right, and then when it's this here, it's trying to move to the left. Okay, so it helps us easy to imagine by looking at a picture. And then it's when something is sitting at the ground, it will just stay on the lower part, right? So this is the equilibrium. Okay, but if I'm on this mountain, on the top of the hill, right, or some upside down bowl, okay, this is, although this is equilibrium, we notice that this is what we call an unstable equilibrium. Okay, so why is it unstable equilibrium? It's because, right, what is something unstable means that if you disturb it a little bit, it will fall down, right? So if you try to balance something on top of a round surface, yes, but when potential energy is increasing, the force will be in the negative direction. Like this, right? Well, if I increase this way, the force will be in this direction, right? But if I increase in the opposite way, the force will be in the right. Okay, it's just by looking at the slope. Okay, so the slope is du dx. The slope here is negative, so therefore the force is positive, and then du dx here is positive, therefore the force is negative, so that it will give you the different directions of the forces. Okay, clear? One more thing I want to mention is that, yes, about the equilibrium point. So as you can see, right, there are two types of equilibrium for one-dimensional potential. Okay, so there are two ways it can have zero slope, when your potential is a minimum and when your potential is a maximum. So when your potential is a maximum, the second derivative is negative, right? And then when your potential is a minimum, your second derivative is positive. So this is what we call, when it is a minimum, we call it a stable equilibrium. Why? Because stable, right, is a minimum. That means if I shift my particle or my object slightly to the left or to the right, then I get a negative slope, so the force will push it back to the equilibrium position. Okay, so if I move the particle a little bit, there's a force to push it back. right? And then if I move the particle the other way, the force will push it back the other way. So it makes sure the force always try to make it stay on the equilibrium point. This is the stable equilibrium. This is what happens when my potential energy function is a minimum. Okay, now look at the opposite case, when the potential energy is maximum. So if I move my particle slightly away, then the slope here is negative, so the force is positive, so you get pushed even further away. Okay, so if I move it to the left, right, if I move it to the left, then the force will try to push it even further away. So this is an unstable equilibrium. Okay, so this is because like it's unstable means any small mistake, you put the object in a slightly wrong place, it will get pushed away. Okay, but if you put your objects at the correct position and must be precise, then only you get zero force, then only you get equilibrium. So it's so sensitive, right? Then it is a unstable equilibrium. Okay, do you follow so far? Okay, so yeah, so imagine this again, right? This is an unstable equilibrium point because I need to put it at a correct place so that it will stay on top, right? If I put it slightly in the wrong place, it will fall down, right? It's because anything that is in the wrong location will give you a force that will push you away. Okay, so that is our potential energy function. So you're asking if du dx is 0 and you have positive what we call the x0. So x0 is the equilibrium position, right? So that means so if so what you're saying is if du dx is equal to 0 at x equals to x0, it is an equilibrium point. Okay, so x0 is the equilibrium point. Okay, so I guess to answer your question, the x0 is the equilibrium point. Okay, and then the two cases I mentioned is that if the second derivative is positive at x0, then this is stable because it's a minimum. And then if your second derivative is negative at x0, wait, it's not 0, then it is unstable. Okay, so yeah, so I think that answers your question, right? Okay, so that yeah, so that is about the potential energy graph, right? So it just by looking at this picture, we can solve a lot of different problems. And actually, yeah, it's a very useful way to imagine. Even yeah, I'm gonna talk about black holes on Friday, right? When people work on research about black holes and they're calculating the orbits, at the end you still look at you still try to read the potential energy graph. You try to find the equilibrium points and things like that. So yeah, so that is a very useful way to help us solve physical systems. Okay, so now let us briefly talk about the three-dimensional case. Okay, so this is 3.4.2. We are talking about the potential energy in 2D and 3D. Okay, so this one Kaheng is asking about the critical point. So GOU? What do you mean? So this is when inflection point, right? Inflection point? Okay, so Kaheng's mention is pointing out is there's another case, right? So let me add to here. So this is where your second derivative is exactly 0 at x0. So this is inflection point. So this is the part where it is neither stable nor unstable. So if you look at this situation, right, it's stable on one side, because if you push it to the left, it will push it back, fine. But if you push it to the right, it will fall down. So I mean, it's you can say that it is stable on one side, but it's not stable. Okay, so there's no special name for it. Is actually there is a special name, but I'm not gonna talk about it in this course. It's called the saddle point. And why is it called the saddle point? You will learn this in calculus, right? Yeah, so it's stable in one direction but unstable in the other direction. Okay, so that yeah, so that is the saddle point. You will encounter saddle point is more common, because saddle point is very rare, because in most physical situation, right, it's either this or this. Only for very, very special situation that you encounter this situation. That's why we don't call it the saddle point. And well, if you're talking about like orbits in astrophysics, right, we do have this situation occurring, but we will not go into detail here. Okay. Okay, no problem. So let's talk about 2D and 3D. So now, what's the difference when I go up to 2 or 3 dimension? Because when we were still in 1 dimension, right, my potential energy is a function of one variable. Okay, so that my force is negative du dx. Okay, let's go to 2D or 3D. Okay, so just 3D enough so that I don't have to keep on writing so many things. If it's in 3D, that means my object can move in 3 different coordinates, right? It can go x, y, and the z direction. So my potential energy function will be a function of 3 variables. Okay, and in 3D, force should have 3 components. So it has x, y, and z components. Okay, so the force is still, the definition is still the same. The force is the derivative of potential, but now I have a derivative of 3 different variables. So this one, for the math students, you are learning this now in your calculus too. For the physics students, yeah, next semester, basically what I'm talking about is the partial derivative. Okay, so since this is a function of 3 variables, then my x component of my force is differentiate this with respect to x. My y component is differentiate this with respect to y, and the z component is differentiate this with respect to z. Okay, so remember, right, force is a vector. So if I write this in vector notation, it has the ijk components. So x in the I component, y in the j component, and z in the k component, right? And then and we plug in all these expressions. So this is negative du dx, I negative du dy, j negative du dz, k. Okay, so if you're learning in calculus, right, this is actually the notation for negative. Okay, so let me write one more line. This is a notation for the gradient operator. Okay, I, j, k, and this is the gradient operator. Okay, so it's the gradient operator acting on u. So why is it called that? Because sometimes it's convenient to write it like this. So you got I d dx plus j d dy plus k d dz. So all these are applying the differentiation on u, and in calculus 2 you will learn this as your gradient operator. Okay, so so it looks scary, but it just means that differentiate x, y, z lah, right? So that's all it means. Okay, so to show you how it works, right, there's 2 examples in the lecture notes. I think I'll just do one of them. Okay, so in the lecture notes there's an example 3.4.4. Okay, and they give you a potential energy function which is x squared y plus z. So given this function, I think there's a question, so let me read the question. I don't remember. Lecture notes. Okay, so this one is pretty straightforward, so you can look at it yourself. for this question, we're asking what is the acceleration when the particle is at the position 110, okay, and the mass is given. So from here to get the acceleration, well, I can get a force from here. So once I get a force, I use Newton's second law, F equals to ma, right? So let's try to get a force. So the differentiation, if I differentiate x only and pretend the others are constant, so it's just 2xy. And then if I differentiate y only, the y will become 1, so I got x squared. And then if I differentiate z only, differentiate z, so I just get 1. Okay, then the force is just the negative of 2xy in the I direction, and then x squared in the j direction, and then 1 in the k direction. Okay, so if you're talking about at the position 110, this means x equals to 1, y equals to 1, z equals to 0. So what happens to my force? So my force is 1 times 1, so this is 2. And then y equals to 1. Well, there's no y here, but x equals to 1. 1 squared is minus 1j. And then k is a constant 1, so it's plus k. Okay, and then using Newton's second law, this is equals to mass times acceleration. So from here, I can get the acceleration is 1 over m, so it's 1 over 0.5, 2i minus j plus k. And this basically times 2, so I got 4i minus 2j plus 2k. Wait, minus, right? So this thing is minus. Okay, so this is acceleration. So we got the acceleration meters per second square. So it's accelerating minus x at 4 meters per second square. In the y direction is negative 2 meters per second square, and vertically minus 2 meters per second square. Okay, so is everyone following so far? Testing the recording. Yes. Okay. Any question? Seems like no. So everyone is okay? If everything is fine, yeah. So I fixed this already, right? I changed. Wait. Yeah. So it's minus k. You're right. Oh, I haven't changed here. So I haven't changed here. Minus. Yeah, but this part already changed. Okay, great. So okay, so so sometimes the notation is like very new. You will learn this more in the calculus 2 and it's scary because I think a lot of students will find this part of calculus 2 more challenging. But for us, it's just to get the xyz components only. So we just need to differentiate xyz to get the correct directions. Then that's all. So for this course, that's all. Okay. So 3.5, we're going to the next part now. This one is about non-conservative forces. Okay. So for conservative forces, right? Remember in the previous class, how can we do this? The condition and the assumption that we make is that the force, this situation works only when the force depends purely on the position x, right? So if f is du dx, then it's a function of x. It does not depend on anything else. So this only works if your force is independent of time and independent of velocity. That is also a factor. Okay, but for here, right, what happens if I do have a time dependent force? So if, let's say, if the force depends on time, okay, velocity, okay, so depending on velocity means including dependent on direction, okay, then or basically anything other than position. Okay, then it is what we call non-conservative. Okay, so for non-conservative forces, we cannot have a potential energy function. So what are the two conservative forces that you guys know? In the end of the previous class, I talked about the spring, right? So spring is, the Hooke's law is F equals to negative kx. So it depends on position only. Therefore, you have the spring potential energy. The gravity, right? For now, we assume near the surface of the Earth. We spent a long time discussing this. Near the surface of the Earth, right? Gravity is constant, mg. So constant, it basically doesn't depend on time or anything else. Then fine, we have a potential energy due to gravity. But if we talk about friction, right? So friction is, it doesn't depend on position. It depends on what you do to it, right? Remember, like static friction, if I try to push to the left, your static friction is acting to the right. If I try to push it the other way, your static friction acting the other way until it reaches the maximum. Basically, friction is direction dependent. Okay, kinetic friction also the same. If your object is moving to the right, your kinetic friction is acting to the left. If your object is going this way, is acting the other way. So kinetic friction, static friction depends on direction, and yeah, depends on direction. And drag force depends on velocity. So all these are non-conservative forces. So for non-conservative force, we cannot define a potential energy in this way. Okay, so what happens to the energy? So I'm going to show you that a non-conservative force will be related to energy being not conserved, mechanical energy, right? So this is where you learn in the high school, where you say that when there's friction, energy is being dissipated as heat or lost to sound and things like that. That is what happens for non-conservative force. Okay, so to write down, let me go back to one dimension. Okay, so let's consider a net force acting on the particle. So we got F net, right? And only x direction only. So I will split into two parts, because if you draw the free body diagram, there's many forces acting on this. So the net force, maybe some of them will be conservative, and this part is non-conservative. Okay, so this part is non-conservative, and this part is conservative. Okay, so let's try to calculate the work done and see what happens to the energy of the system. Okay, so let's calculate the work done due to this net force with respect to dx, and of course, let's say the particle going from position 1 to position 2, right? So F net is the sum of two terms. So basically, I got the integral of F, the conservative one, and the integral of the non-conservative force. Okay, so this part is conservative, right? And we have done this in last week. It is equals to negative of potential energy plus potential energy 1. Remember, right? We define this as the negative derivative, right? So this part we cannot define a potential, because for different types of motion you will get different final answer. Okay, so this is why we cannot get a unique function of x. Okay, so it will depend on time, so we don't know. It depends on how long does it take, it depends on how fast or what is the direction it's moving. Okay, so, and then also in the previous classes, we have also learned about the work energy theorem. Okay, so according to the work energy theorem, this is equals to the change in kinetic energy, right? So this is the change in kinetic energy. And then let me write out the full equation. So this is the change in kinetic energy. This is U2 plus U1. And this part is the, well, is some number. So let's call this a work done due to the non-conservative forces. So it's W non-conservative, right? So you see here that there's no energy is not conserved, because my final energy of the system, if I move U2 to here, and if I move K1 to here, this part will give me the total initial energy of the system. This is the total final, total initial, and then there's a discrepancy. They are not the same number. Okay, so from this we find that this part, right, is the final mechanical energy. Okay, and then this part is the initial energy when you start the motion. And this is the difference. So this is the work done due to non-conservative forces, right? So work due to non-conservative. Okay, so itchy, sorry. So the energy is not conserved over here. Okay, so yeah, so let's look at the possibility. It could be positive or it could be negative, right? So how to write this? Okay, so non-conservative force, right? If, as you can see, right, if this is a negative number, so the final energy is less than the initial energy. If it's a negative number, it will reduce the energy of the system. So if it's negative, that means total energy is lost from the system. Okay, and if it is a positive number, if this is a positive number, I add to the initial energy, the final energy becomes higher. So that means there's energy added to the system. Okay, and if it's zero, then energy is conserved, of course. Okay, so that is the different possibilities. Okay, so everyone is following so far? Am I going too fast or too slow? I feel like this one is something that is learned in the high school before, right? So it's not the first time you heard this about energy, and also regarding energy loss. Okay, so am I online? I'm online. Yeah, I'm recording. Test. Okay, yes. Yeah, so I'm relying on you guys messaging here to at least make sure I'm not disconnected or something. Yeah, the equipment here is very the equipment I have now, like the mic problem and stuff, it is very hard to control and quite unpredictable sometimes. So if everyone is yeah, that's true. During high school, we consider the ideal model. And well, partly because it's the easier situation, right? And it's sort of approximate situation that is good enough to solve many problems. Okay, so if everyone is okay, then let's shall we do an example? Okay, so yeah, for this example, this is one example for a non-conservative force, right? So I have a 2000 kg object with broken cables, and then it's falling at 4 meters per second, and then it contacts with a spring at the bottom of the shaft. The spring is intended to stop the elevator compressing by 2 meters. Okay, so I got the compression. Well, let me copy down the information. Okay, so the mass of the object is 2000 kg, and the initial speed, I will call this u, is 4 meters per second. Okay, and then I have the spring compressed by 2 meters. Okay, 2 meters, and as that additional safety is there's a brake. Okay, so there is a brake, and during this process, so it will give you a frictional force that already gave you the number, so we don't need to calculate the formula for friction. Is 17,000 newtons. So what is the force constant of the spring? Okay, so we assume that the force is constant 17,000 throughout the process, so it will make us easier to calculate, right? So if we go by conservation of energy, okay, so initial energy, okay, so let me follow the formula on top lah, right? So let's say the final energy is equals to the initial energy, and then plus the non-conservative work done, right? So what is the final energy? So final energy is what happens, so is that it's falling vertically, right? So it's falling vertically, so you have, and then it compress the spring. So it will, when it compress the spring, I got half kx square, and then I got the height, so it's got mg, the final height, and then that's all, right? I want the elevator to stop, so there is no kinetic energy, so this is all the final energy that you want. how about the initial energy of the system? So initial energy of the system is starting to fall at some initial height, right? And then is moving at velocity u, so I got the kinetic energy half mu square. Okay, and then I want my non-conservative work to remove energy from the system, and the question gave you the magnitude, so I expect to remove by 17,000. Okay, so from here I can find the required kx, because I got half kx square, so this is half mu square. So if I move this over, so I got mg, the change in the height, so my final height minus the initial height, right? So the height information can be gotten from the question. Okay, so yeah, so it's basically 2 meters, right? So it's 2 meters, and just plug in 2 meters over here. So this is 2 meters, and then remove 17 friction. This one is 4 meters per second. This is also 2 meters. So from here we can calculate the kinetic energy by solving for k, not kinetic energy, the spring constant. Okay, so the spring constant is going to be this number. So 1.06 times 10 to the power 4 newtons per meter. Okay, follow so far? Clear? So this example is just easy, like it's a basic example, and just to demonstrate the concept. The next example is probably more common and more interesting, because it makes a few different concepts together. So let's go to example 3.5.3. This is the one that I want to solve and spend a bit more time on, because this is probably something that is slightly more new. Okay, 3.5.3. Any question? The final energy. The final energy is so maybe, yeah, let's draw a picture. Okay, so let's say the initial moment, and then the final moment. Okay, so you just need to keep track. What at the final moment, what are the energy? What is the situation? So the initial situation, I did not explain the example more precisely, but because I forgot to say that this is just starting to touch the spring. Oh. So initially there's zero spring energy, and it is moving at velocity u, so it have half mu square, and then it has the height mg h initial. Okay, so that one you understand. You want to know the final, right? So the final is it has been compressing the spring, and it has stopped. So it has stopped. The velocity is 0, and then the height is lower than the previous height. So I got the final height down here. Okay, so from here to here, the displacement is 2 meters. So the change in height is 2 meters. And the compression is also 2 meters. So x is also 2 meters. Okay, so what are the energy of the system? So I have a potential energy, there's no kinetic energy, and there's a compression of the spring. So I got half kx square compression of the spring. So there's a spring potential energy. Clear? Okay. Where's all this email? Is yes, okay. Why can we directly use as the work done by I forgot. This is the force. This is the force. My mistake. This is the force. So I need to times the displacement. So the displacement is x. So this is 2. So that is what you mean, right? Yeah, that's my mistake. This is the force. What do you mean? Right? So this the force of friction is in Newton. So you times this to get the displacement. Yes, correct. You're right. Okay. Okay. So this meme I don't know. Yeah, I'm not man of culture enough. Okay. Yeah, I will skip this. You take a look at this yourself because I want to do this, right? So this example is about the car moving horizontally on a block. So let me draw this picture first before I read the question. Okay, so I have a car, and then I'm moving at some initial velocity u, and then it executes a circle of radius r. Okay, so this is the situation, and let's read the question. All right, so everyone's ready? So let's do this question. Right, so I have a car initially moving at this velocity entering a loop track. What is the minimum velocity such that the car is able to make it through a full circle? Okay, so how do we solve this problem? This one is like a, yeah, so this one you imagine, right? You have seen this like a roller coaster, right? Or a roller coaster or some motocross situation where you have a motorbike that is driving fast enough that it can actually go one full circle without falling down. So what is the condition that you need to avoid falling down, right? And the condition is you must have a non-zero normal force. You need to be pressed against the surface so that you do not fall down. So that is the requirement. Okay, so let's try to solve the situation. Let's draw the free body diagram when it is on top. Okay, so why do I solve this problem on top? Let's think about this situation. So when my car is driving here, right, it's still okay, right? It's still no problem to touch the ground. Okay, so the most dangerous point is when it's at the top of the circle. So when it's at the top of the circle, right, it is the most likely case where it will tends to fall down. So we shall solve the situation where it is on the top. Okay, so this is, if we can make it through the top part, then the rest will be okay already. So this is the most dangerous point. So let's see what happens when it is at the top point. Okay, so when it is at the top point, what are the forces acting on the on this object? So let's say this object has mass m, right? So it's going to have a weight mg. It is touching the upper surface, so that I have a normal force that is acting down. Okay, so the net force acting on this object is n plus mg. So this is my net force along this downwards direction, and since this is a circle, this is a circular motion, so the net force is equal to the centripetal force. So this is equal to mv squared over the radius of my circle. Okay, so this is my first equation that I have over here. So this one is solving using the Newton's law. So this one is like we are still in chapter 2. So now I have two unknowns because I don't know what is my normal force and I don't know what is the velocity here. The velocity depends on what is your initial velocity. So this is where we use conservation of energy. So by the conservation of energy, so mechanical energy is conserved here because there's no friction now, right? This is my initial situation and this is my final point for my calculation, right? Of course it will continue after that, but for my calculation I'm considering these two parts. So what is my initial energy? So initial energy is just the kinetic energy, half mu squared. Okay, so total initial energy should be equal to the final energy. So what's my final energy? My final energy is, well, my kinetic energy will be having some final velocity, which is an unknown, right? It's some number which we don't know yet. And then, well, it climbs up by a potential energy of mgh. So I got mgh over here. Okay, so the potential energy will increase because I'm going up against gravity. So what is the height? Is actually 2r, right? So we can actually solve this question. Notice that the mass all will cancel, and if I multiply 2 up by everywhere, so I got u squared v squared and then 2g times 2r. So I got u squared is equal to v squared plus 4gr. Okay, so I have now two equations, a second equation for v. So v is unknown, but I can substitute into this over there. Okay, so what I got now is, well, this is equation 2. So what I can do is, I have two equations and two unknowns. right? So let's see what happens if I substitute 2 into 1. So if I substitute 2 into 1, right, I got on the left hand side n plus mg, and then this is m over r. So if I plug in v, I got this one is 4gr. So I can simplify this equation. I got mu square minus 4mg. Oh yeah, this part is divided by r. I forgot to divide by r. Yes, okay, so it looks good. So that means now I got, that's another mg here. So I can bring this over, right? So it becomes 5 mg. So I got n is equals to mu squared over r minus 5 mg. So this is the normal force. This is the equation of the normal force that the object is experiencing. Okay, so notice that this normal force depends on my initial velocity. So if my initial velocity is higher, the normal force when it reaches the top is higher. Okay, when it gets lower, the normal force will become lower. What happens when the normal force becomes 0? Okay, so when u reaches some minimum number, the normal force will become 0. Normal force becomes 0 means the object is no longer touching the surface. Not touching means it fallen down, right? So object not touching surface. So it is fallen down, right? So if you're not, there's no normal force means you're not touching. You're not touching means you're falling, right? You have fallen off the loop of the surface. So we want to calculate what happens here, right? So so I got 0 is equals to mu square minimum over r minus 5 mg. So when it's 0, I can cancel the m. So my u minimum is 5gr. And then you take the square root. Okay, so this is the minimum velocity. So any higher than this is fine. Then you have a non-zero normal force, right? As long as you're higher than this number. So this is the minimum condition that you need to avoid falling off the surface. Okay, any question? Not 100% in the falling out. About to fall down. Sometimes objects are in contact, but it's not causing any force. Yes, it is the critical moment, right? It is a critical moment where it's about to fall down. Yeah. So yeah, that's true. So it's correct. Right? Makes sense, right? So so what you want is to guarantee the object staying on the surface. You want n to be greater than 0. Then definitely it will stay on the surface. When it's still moving. Yeah. You're right. So it's just the critical point. Yeah. So it's still moving, right? It's still moving, but it's not touching. So it's that is the critical point we are talking about. Okay. Okay. So what time is it now? Okay. So slightly early, but we have ended chapter 3 already. So I think I will start talking about chapter 3 a little bit before we take a break, right? Just so that because it's still a bit early for the break, and unless anyone have question to discuss. No question. So if everyone is okay, then so we will do more of this type of questions and examples in the tutorial, right? So for now, let us go to the chapter 4. So for chapter 4, we will start a new chapter. We start to talk about momentum. Okay. So momentum is again something that you have learned in high school, but also I think in the ideal situation, right? But for now, let us try to talk about and discuss momentum. So we are in chapter 4 now, and we are more specifically talking about linear momentum. So linear momentum is for objects moving with linear motion, because we do not talk about angular momentum yet. Angular momentum is later. Okay, so firstly, let us start with the concept of linear momentum. And let me define what is linear momentum. So momentum is a very interesting concept, because the mathematical structure of why there is momentum is actually very deep and interesting, right? There's a very interesting reason why we talk about momentum, because I define momentum now, right? It looks very random and boring, right? MV. So why is it so? And the reason you will learn when we go to a higher level classical mechanics course, where we talk about Lagrangians and Hamiltonians. That is where all the interesting stuff comes in, and that is we really see what is the real concept of momentum. But for now, right, we are still staying in a boring mode. That is, we are talking about an object of mass, let's say some m number of kg, right, and is moving at velocity v. Is given by m times v. So this is momentum, right? Linear momentum, and we use the symbol p to denote momentum. So in fact, why is it called p? Also, you start to notice why when we learn more things. NV momentum, music video momentum. Or is there a band called Momentum? Which I don't know. Yeah, momentum. Okay, so or what's NV? Yeah. So this is momentum, right? And so but right now so if you're learning this for the first time, or at least in this course, it's a new physical quantity that we are learning in this course. So let's talk about the units. Okay, so the units, okay, so what's the units of momentum? It's easy to get. It's just the units for m and then the units for velocity. Well, the dimension is mass, and then velocity is LT minus 1, right? So from here we get the SI unit. It is no special name. It's just kilograms meters per second. Okay, so this is the unit for momentum. Okay, so so you guys know what Kaheng is talking about or something. Okay, so that is what time is it now? Okay, so let me relate this to Newton's law, right? So why, okay, there's two reasons why we define momentum in this way. Okay, yeah, because I can't wait to teach you guys the second year mechanics course, because that is where the interesting stuff comes in, right? And but another reason why we define it this way is because this is how Newton originally stated Newton's law. So we can express Newton's law in terms of momentum. Okay, and Newton's law is actually the change of momentum. So let's start with the Newton's law that we always use is F equals to ma, right? And then our acceleration is basically dv dt. Okay, and of course I can try to express this in terms of momentum. If I can put the m inside, I can do that if my mass is a constant. Okay, so object has constant mass, and this is my p, right? So in other words, Newton's law in the language of momentum is dp dt. So the Newton's second law in terms of the momentum says that force is equals to rate of change of momentum. Okay, so that is basically the idea of the momentum. Oh, sorry. Wait, it's already high. Yeah, you can see this, right? Anyway, I'm going to leave this up here. When will we learn the angular momentum? Yes, chapter 5 and 6. Okay, so it's actually chapter 5. No, chapter 6. So chapter 5 and 6 is actually one big chapter about rotational motion, and I split into two because it's quite a long chapter. And yeah, so now it's almost 11 already, so let's take around 5 to 10 minutes break. And yeah, so yeah, let's say 5, and we'll probably start a bit later than that. Okay, so let's take a break for a while. I will stop recording, and I will stop recording here as well. Okay, so I'll stop recording. Test. Okay, great. So yeah, momentum. Okay, so for momentum, right, so force is the rate of change of momentum. Okay, so it is something to do with changes. So that means what we want to an important quantity is the actual total change of momentum, which we will get as what we will define as an impulse. So this is another quantity, impulse. Okay, impulse is just basically the change in momentum. Okay, so how much does the momentum change throughout a process? So we give it a symbol J, right? It's basically just the change in momentum. So if momentum is not a constant, then you need to integrate over the changes. Okay, so it's integral of dp. Now, what does this mean? Well, F is dp dt. So integrating this is just means that I'm integrating force with respect to t, right? It's basically bring the t over and then you integrate both sides. So we have the this is how you calculate the impulse of an object. So this is from t1 to some initial time to some final time. Okay, and we can imagine that the impulse is the area under the ft graph. So if I can plot the force, right, if I let's say I'm only talking about one dimension. Okay, so one dimension, then let's say in the x direction, and then if I see how the force changes in time, then maybe it's not a constant, right? Time dependent force, this one is definitely non-conservative. Then then the area from between t1 to t2, the area under the graph is your impulse. Okay, so the area under the graph is the impulse, and another quantity we want to define is the average force. So average force is basically just the total change of the force divided by the total time. So if this is my delta t, then my average force is just the change in momentum, the impulse, divided by time. Okay, so from here we see like this is something similar, right? If I take the limit t goes to 0, I will get the actual force, the instantaneous force. Okay, which is our original force is taking the limit delta t going to 0, delta p, delta t. So this is, you get back dp dt. Okay, so this is another like coming to the concept of force from the other direction, right? Remember, this is how we learn about average velocity and instantaneous velocity, right? So it's the similar idea. Okay, so this is what we have, the average force. Now in your calculus, right, if you are taking calculus 1, you will learn about the mean value theorem. The mean value theorem guarantees that my average force is somewhere inside here. Okay, somewhere inside here, right? It's not out of the range of what is in the graph. So that one is from the mean value theorem. Mean value theorem of your calculus. Okay, so yeah, just I mean, it's not a big deal. I just want to mention so that it's something familiar to you, right, in your other course. But for us, is average force, right? It's just dividing the total change in momentum divided by the total time during the process. Okay, so everyone follow so far, right? Okay, so it looks okay so far. This one is yeah, as Probably most of us have learned this in the high school. Now, I will jump ahead to talk about the conservation of momentum, because this is where it's more tricky, right? 4.2, conservation of momentum. Okay, so in your high school, you learn that momentum is conserved, energy is conserved, right? Right. Last week we have learned, starting from Newton's law, exactly why energy is conserved, and now again starting from Newton's law, we will learn exactly why momentum is conserved. So as you notice, right, everything actually comes out from Newton's law. So Newton's law is the fundamental one, but what we are doing now is like we are manipulating and rephrasing and excuse me, rewriting Newton's law to make our calculation easier and to extract certain concepts out of it. Okay, so so this is about the conservation of momentum. So I just remember last week I sent an announcement, right? There's a paper talking about the philosophy of Noether's theorem and why you have conservation laws, right? Why is momentum conserved? Why is energy conserved? And later, why is angular momentum conserved? So if you're interested, you can take a look at that. It's not very mathematical, so it's just a lot of explaining. So it should be quite interesting to read. But for now, let us try to understand conservation, try to derive the conservation of momentum from Newton's law. Okay, so why do we want to, now what is the main purpose of learning conservation of momentum? It's very useful because we have already learned Newton's law in drawing free body diagram. Once we identify all the forces, we can calculate the acceleration. Once we calculate acceleration, we can use our other kinematic equations to calculate the motion of the other quantities, right? Velocity, position, and things like that. Okay, so far we have learned how to do those things, but we haven't solved collision problems yet. Okay, so we are just talking about object moving this way under this force, fine. But what happens if you have two objects, they hit each other and they collide? Okay, so if you play billiard, right, or snooker is collision all the time, right? You hit one ball and then the ball will collide with another ball and then it will go off into different directions, right? So playing snooker, that is collisions. So can we solve this type of problem? If you think about it, right, drawing the free body diagram, this is like a time dependent force, because if it's moving, there's no force, right? Suddenly colliding, there's a normal force. Then after collision, no more normal force. So this is definitely a time dependent force. And how are we going to solve this type of problem? Okay, so let's try to think about this. Okay, the idea is, if you draw a free body diagram, you have different diagrams for different times. For example, I have object 1, object 2. Okay, this is before colliding. Okay, so it's before colliding. So let's say it's coming towards each other. Let's say I'm having some initial velocity u1 and some initial velocity u2. Okay, so if before colliding, right, so firstly we will assume no external force. So that means it's moving on a smooth surface, there's no friction everywhere. It's on a horizontal surface, so there's no gravity. So we will worry about gravity later, but for now, we have no external force. And then after that, what happens when they collide? So when they collide, this is during collision. Okay, so this is during collision, object 1, object 2. And after colliding, they will move in different directions. So let's say my final velocity v1 and my object will go off the other way, v2. Okay, so what most of the time we try to predict what happens after collision, or maybe we observe something after collision, we try to calculate what happens before that. Okay, so this is what we want to do. Okay, so this is our challenge, which is not so easy, because this is only one moment where there is a force. So let's try to figure this out. Okay, so let's try to draw the free body diagrams during collision. Firstly, starting with object 1.
free body diagram. Okay, so object 1 free body diagram, what's happening to object 1? So let's look at object 1, and what are the forces acting on object 1? So it is touching object 2 during that moment. So during that moment, it is touching object 2, so there's only one force coming from object 2. Okay, so coming from object 2 perpendicular to you, so it's like a normal force, and I will write this as force coming from 2 acting on 1. Okay, so the only force acting on object 1, the only net force is this force, and by Newton's second law is equals to mass times the acceleration of object 1, and it's only this force, so this is F21. So I'm writing in the vector form, so the direction is encoded inside the vector, is to the left, so it's going to be some negative I number lah, but I don't care. First I'll just write the whole thing as F. Okay, so this is MA, and we have also seen just now, right, I have rewriting the force as the rate of change of momentum, so this is dp1 dt. Okay, so this is equation 1, right? Now how about object 2 now? So I draw the free body diagram for object 2. Okay, yeah, so object 2 free body diagram, and oops, object 2 free body diagram, and let's look at the forces acting on object 2 now. Okay, so for object 2, right, we don't care about 1, we just know that object 2 is touching object 1, so this is F coming from 1 acting on 2. Okay, so here we can see Newton's third law coming in, right? This is object 1 and object 2, so they touch each other. This is an equal and opposite force, right? But basically the net force acting on object 2 is this force, and then this is dp for 2. This is the rate of change of momentum for object 2. Okay, so this is equation 2. So what I can do now is I'm going to take equation 1 plus equation 2. What do I get? So on the, I will write the momentum first. It's basically rate of change of momentum for 1 and rate of change of momentum 2 plus together, and then I got F21 plus F12, right? So let me just check. I'm recording. Test. I'm still recording. Okay, sorry. Always check. It's important. Then, okay. I was saying, right, this is Newton's third law. These are equal and opposite reaction. So they are equal and opposite by Newton's third law. These are equal and opposite. So what do I mean is, if you're equal and opposite, they cancel each other out. So this is equals to 0. Okay, so so this right hand side, the whole thing is equals to 0, and then on the left hand side is, I can write this together as the rate of change, because derivative plus together is the same as plus together first, and then you differentiate, right? So on the right hand side is equals to 0. Okay, so what is this? So this is momentum 1 plus momentum 2. So we call this the total momentum of the system. So this is the total momentum. Okay, so let's call the total momentum of the system as P1 plus P2. So the equation that we got now is that dP total, the derivative is equals to 0. Okay, so what we got now is that what we have just derived is that under this situation, in particular, we assume there's no external force. So if there's no external force, then there's no other force. There's no other net force here, no other net force here. From here, we can calculate that the dp dt is 0. So if something, when you differentiate, becomes 0, means what? It is a constant function, right? Constant function, when you differentiate it, it becomes 0. So momentum is constant. Okay, so from here, we conclude that total momentum is constant. Another way of saying is that conservation of momentum. Okay, so from the conservation of momentum, what can we conclude, right? So the total momentum is constant, constant due to this collision. And over here, definitely the velocity is constant, the mass is constant, so it's always constant, right? So from here we can calculate the P1 plus P2 is equal to M1U1 plus M2U2, right? And then for here, okay, after collision, what is the total momentum after collision? The total momentum is P1, P2, and then is equals to M1V1 plus M2V2. Okay, so what I'm trying to say to you is that this part is definitely a constant because nothing is happening, constant speed before colliding. So total momentum is this number, right? And then during collision, this thing happens, but we have proven that momentum doesn't change during this collision. So the total momentum will be the same number. Okay, so P total is equal to P1 plus P2. Okay, then the velocity at this instant is changing, so the formula for V is complicated here, but so I don't care. Okay, and then over here, this is the total momentum. So if this momentum doesn't change here, it will continue being the same. So the total momentum here, here, and here is always the same number, same value, same vector, total momentum. Okay, the individual momentum might interact and change, fine, but the total is always the same. Okay, so you get my point? The range of thanks, Kaishan. The range of momentum is larger than the energy one. Well, what do you mean by range? You mean the situations where momentum is conserved, right? The situations where momentum conserved, well, it's hard to say lah. It's sometimes yes, sometimes no, because in the problems that we solve, right, we will feel that we use conservation of momentum more frequently than conservation of energy. That is true, okay? Because this situation is quite general. So in that sense, yes, it is more momentum is more commonly conserved than energy. I think that's what you mean, right? Yes, in small particles. So we are still assuming they are particles for now. So these are like object particles. So when they are large, then we need to consider the size of the object. Then it starts to become complicated. But then you can treat them as the center of mass. So that one we will come to that later as well. Okay. Okay. So yes. Hang on. What happened? What is, yes, we treat them as point mass, correct. What is the difference between F1 net and F21? The difference is that they are equal and opposite. You remember the Newton's third law, right? This is the force that is, the difference is this. F21 is the force experienced by object 1. If you're object 1, this is the force you experience. This F12 is the force experienced by the other one, the other force. But because we know Newton's third law, we know that the magnitudes are the same. Magnitudes are the same, but the direction is opposite, exactly opposite. So that's what I mean, F21 and F12. Wait. Oh, I just read F1 net and F21. Is that what you're asking? F1 net is. Oh, sorry. I just read carefully. F1 net and F21. They are the same. I mean, F1 net is nothing special. I just mean net force. Okay, so what I mean is the net force. I just writing some extra. I think that's what you're asking, right? There's no difference. F1 net it just generally means me asking the question, what is the net force acting on object 1? And then from the free body diagram, we determine that it's only F21. Okay, so I think that's so that's what I meant. Okay, so right now at the moment we have shown that momentum is conserved, but there's an important assumption that there's no external force over here, right? We can get 0 because there's no other force here. If there's some other force here, we need to plus something here, plus something here. And then when you plus something, only the interaction will cancel out, but there's other forces in this situation, then it's no longer conserved. Okay, so that is hopefully right now we are convinced as to the reason why momentum is conserved for collisions. And I'm sure most high school, right, they just give you the formula and they just tell you momentum is conserved. Maybe they explain why, but we forget. So it's the reason why is actually coming from Newton's law, and second reason is no external force. Okay. Okay. So let's do an example. So an example, let me bring this up for the, wait, did I press OBS? Yes. Okay, so let's bring an example. So in the lecture notes, I calculated some typical magnitudes of momentum lah. For a moving car is this much. For a running human is much smaller. Okay, so you can get the idea of like the different ranges of momentum. Okay, the previous example is just like applying the formula only, so I think everyone should be okay with that. This one also is pretty straightforward, but it's an important method to learn. I mean, it's important lah, right? If you know how to do this, then every other question is around the same method. It might get more complicated, but the basic method is the same. What am I talking about? I have two objects, right? They give you the mass for this one, mass 1 and mass 2, and they give you the initial velocities. After collision, this object moves to the right at 2 meters per second. We just need to calculate v1, the velocity of object 1 after collision. So how to calculate that? Okay, so let's draw the situation, right? We have object moving on a smooth surface. That's how you know there's no external force, right? The first object is moving at 2 meters per second to the right. Second object is moving to the left, so I should put a negative sign here. Okay, so and then the mass is 0.5 and 0.3, right? Yeah, no need to write, you get the point. Okay, so after colliding, after colliding, I don't know what is V2. Okay, actually I draw the arrow on the question, but it's just an assumption. Actually, we do not need to assume the direction. Actually, the calculation will tell you whether it's positive or negative, right? So, but what the question did tell you is, after colliding, the velocity of the second object is 2. So we shall use the conservation of momentum. So since we are all in the x direction, we just draw one component. So m1 v1, m2 v2, m1 v1, m2 v2. Okay, then we just substitute in the values. So the first object mass is 0.5 kg, is moving to the right at positive 2. Second object is 0.3 kg, is moving to the left, so I put the negative sign here. Okay, and then m1, okay, still 0.5. v1 is something that, v1 is the unknown, right? So v1 is the unknown, and then v2, object 2 is 0.3, and after colliding is moving to the right, so I put a +2 here. Okay, so this number should be able to calculate, right? So 0.5 times 2 is 1. This is minus 0.6, so on 0.4 on the left, this is 0.5 v1, and then this is positive 0.6. So from here you can calculate v1 to be a negative number, 0.40 meters per second, right? So the answer gave you negative. That is how we know is moving to the left after collision. Moving to the left at the speed 0.4 meters per second. Okay. Any questions so far? Everyone following? Right? Okay, so now, yes, this looks very easy. But now I will go to it will start to, you will see like the equation becoming longer and longer, but trust me, the basic method is still the same, still starting like this. Okay, so what I'm going to talk about next is about elastic and inelastic collision. So this is 4.3. This is focusing on collisions in one dimension. Okay, so and 4.3.1 is talking about elastic. So what is elastic collision? Okay, maybe you have heard of elastic collisions before in your high school, right? But so let's do it here again. So what is elastic collision? Elastic collision is, well, generally speaking, collisions is where we assume the momentum is conserved as long as there's no external force. So momentum is conserved. But for elastic collision, right, elastic collision is also where a specific situation where the kinetic energy is conserved. Okay, so why is it giving the name elastic collision? Usually the reason is because if we talk about like a rubber ball, right? So if you throw a rubber ball and it hits with another rubber ball, this rubber ball is like elastic, right? So they bounce off, and then you realize later that the kinetic energy for this situation is conserved. Okay, so that is where the kinetic energy is conserved. So let's try to think about why. Okay, so the kinetic energy, the reason why kinetic energy is conserved, right, is because, well, this is only kinetic energy, right? This is not talking about total mechanical energy. Mechanical energy involves potential. So it involves potential, but here we only want kinetic energy. So we want to have a situation where there's no potential energy involved. Okay, even if there's potential energy, we want them to be constant. Okay, so it's either no potential energy or potential energy is unchanged before and after collision. Okay. Yeah, so this statement is actually, it's a loaded statement. There's a lot of things to think about. So if you're confused by anything, so ask me in the chat. But otherwise, this is the reason why kinetic energy is conserved. Okay. Maybe I should write some equation to make it clear. So the energy of the system is the kinetic plus potential. Okay. So if there's no friction anything, then this is conserved. And if this potential energy is also constant, then this is then the K will also be constant, right? So E minus U equals to K. Okay, so basically, how do I want this to remain constant? Potential energy must be the same before and after. If the potential energy changes, it will affect the kinetic energy. Okay, so this is how you can get kinetic energy conservation. And momentum conserved, the reason we have just seen just now, is as long as there is no external force. Okay, as long as there's no external force, or so let's leave it like that first. There's more things to comment on. I think I will comment about it later. All right. But I think what the more important thing right now is to try to derive a formula regarding elastic collision. So this formula will make your life much easier. Although the derivation will involve long equations, but it will make your life easier. Okay. So let's see the time. So everyone is okay, huh? Everyone is fine. Okay, so let's talk about elastic collision. Okay, so since for elastic collision we have conservation of momentum and conservation of kinetic energy, we can use this. Okay, so firstly, let's start with momentum. So since momentum is conserved, right, let's talk about two objects colliding also. So I got m1 initial velocity and m2 initial velocity. This is the total momentum before collision. After collide, we still have the same. Maybe the velocity change but the total momentum will keep it the same. Okay. Now to derive the formula later, I want to purposely rearrange this equation. So I want to bring all the m1 together. So the m1 I bring over here, so I got u1 minus v1. And then the m2 I bring over there, so I got m2 v2 minus this is u2, right? So this is equation 1. Okay. That's brightness. Okay, so this is for momentum. And also for elastic collision, right, kinetic energy is conserved. So let's talk about the kinetic energy. So kinetic energy of the system is half m1 initial speed square, half m2 initial speed square. So kinetic energy of object 1 plus kinetic energy of object 2. And is conserved. So we expect after colliding, even if they have a different final velocity, the total should be the same as before. Okay, so let's try to simplify this equation. So I will cancel all the half everywhere. And then I try to bring the m together. Okay, so the m1, I bring this here. So m1 got u1 square minus v1 square on this side. And then m2, I bring that over. So I got m2 v2 square minus u2 square. Okay, so I can actually simplify this equation because this one can be factorized, right? This one, if you're familiar with this, the mathematics, this one is actually this thing times this thing, right? You do the same thing on the other part. So it's this thing and this thing, right? So if you expand this bracket, you just get this. If you expand this bracket, you just get this. So I got my second equation over here. Okay, so now I can derive a simple formula if I take equation 2 divided by equation 1, because there's a cancellation happen. So this part is exactly the same as this part, right? This part is exactly the same as this part, so I can cancel them away. So if I take equation 2 divided by equation 1, right, if I take this divided by this, so this stuff will cancel each other. Then I'm left behind with something very simple. It's just u1 plus v1 is equals to v2 plus u2. Okay, so this is a formula that is obeyed by particles under elastic collision. Okay, so basically on the left hand side, you notice that how to remember this formula. This is object 1 velocities. Okay, so object 1 initial velocity plus final velocity for object 1, and then this is the same for object 2. Okay, and this formula is obeyed for elastic collisions. Okay, so we can use this equation as long as we know that the collision is elastic. Okay, so does everyone follow so far how we get this formula? Okay, but if you're answering a question, if you know it's elastic, then you're allowed to immediately start using this formula. Okay, it's fine. It's fine. Okay, so does anyone have any question? Okay, so I think everyone should be okay for now. Then let us continue finding let's try to make use of this formula. Okay, so what I can do is, well, elastic collision is a very powerful formula that I can actually use it to predict the final velocities of a collision. Okay, so let's say I have a situation, right? So I got m1 and then u1 and then m2 and then u2. Okay, so given initial velocities and masses, we can predict the final velocities after collision. So this is what I'm going to do next. Okay, so let's Yeah, so let's start with this. Okay, so now to predict, right, so let us use the conservation of momentum again. So for conservation of momentum, I have m1 u1 plus m2 u2, and then m1 v1 plus m2 v2. Okay, so right now it's unknown, but I can actually calculate. What is v1 and what is v2. Okay, so how to calculate, right? So we will use our elastic formula. Which is to say that my elastic formula is this one. Okay, so it's u1 plus v1 is equals to v2 plus u2. Okay, so it's actually a second equation, right? Right now I have two unknowns, and then I have two equations. So I can eliminate v2 to get v1. So v2 is actually u1 minus u2 plus v1, right? Then what I can do is I will substitute equation 2 into 1. And let's see what we get, right? So equation 1 is here. So what I'm going to do is I will take this and then put it into here. So let's see what we get. m1 u1 plus m2 u2, and then m1 v1, and then m2 times everybody here, right? So m2, m2, and m2. Okay, then I can solve for v1. Okay, so solve for v1. Well, all the other stuff I bring it to this side. So so I have well, this is related to m1, and wait, is there something wrong? And then this is related to m2 and u1. So if I bring this term over, I got the difference in masses u1, right? So if I bring this term over here, I got this, and then these two are the same number, so I bring this over, it becomes plus, then I got plus 2 m2 u2, right? And then this one is just, I can factorize because I want to find v1, so m1 plus m2 v1, right? So finally I have a formula for the final velocity. So final velocity, I just divide this thing down, which I got my answer now. So m1 minus m2 u1 plus 2 m2 u2, then divided by m1 plus m2. Okay, so see, this one is like a very general formula, right? For any mass they didn't say, for any velocity they didn't say, but later when you get the number, you can just this will tell you the final velocity of object 1 after collision. Okay, so yeah, let me check again. Am I online? Can someone say something? Yes? Okay, great. Yeah, must check. This is important. Okay, yes. So yeah, okay. Oh, Kaishen, so you're saying this is me realizing I'm offline, is it? Okay, so okay, so now we got the final velocity v1, but again you can do the same method, which I will not repeat again. So using the same method, you can get the same formula for velocity 2. So using the same method, just that you eliminate v1 and then you solve for v2. So you're solving for v2, the formula you will get is just m2 minus m1 u2, and then 2 m1 u1 divided by m1 plus m2. Okay, so we have found the final velocities, the general formula for a final velocity after collision. Okay, so everyone is following, right? I'm not going too fast, right? Because last week you guys said I was too rushed, but for today chapter is okay, is it? Is that the reason why? The tutorial was too rushed, I think. Okay, great, thanks. Okay, so this is a general formula, and let us try to, like I was saying last time, right? Especially I'm doing Newton's law is when we derive a formula, let's see whether it reflects our reality, because we've been doing a bunch of math, right? But in physics, the math should give some answer that actually happens in real life. So let us consider some special case. Okay, so let's consider a special case. Let us imagine a situation, right? Some situation that we may have seen before. Let's say, right, elastic collision, right? It must be elastic collision. And so let's say I have a very small ball, right? And then it collides with something very heavy, like a car, right? Or a big box is enough. Okay, so a car, big box that is not moving, and I have a small tennis ball, right, or ping pong ball. If it collide, it will be elastic, right? Ping pong ball, tennis ball, most of the time is elastic. Okay, so let's imagine that collision, right? So what I'm trying to say is, let us calculate a small moving mass colliding. Check the time. Colliding with a heavy mass at rest. Okay, so what is happening here is a small moving mass. So let's say the small moving mass is m1 and a heavy mass is m2, and the heavy mass is initially at rest, so u2 is 0, and the small moving mass, so u1 is non-zero, and then they collide. Okay, so because m1 is very much smaller than m2, so I write this equation: m1 is much smaller than m2. Okay, so what happens when they collide? Okay, so we can sort of, in our everyday experience, right, if we throw a tennis ball against a big box, right, the big box will not move, right? It's gonna stay there, right? If you throw a ball against a lorry or a house, right, the house will not move. Okay, so our final answer should have a final velocity of the house that is not moving. So let's apply the formula. Okay, so the formula that we just derived, small mass velocity after collision. Okay, so for the small mass velocity after collision, which is v1, right? So the general formula is m1 minus m2 u1 plus 2 m2 u2 m1 plus m2. Okay, so I know time is running out, but please bear with me. I will finish this and then end the class soon. Okay, it's very interesting because, okay, let's see what happens if I try to make use of this fact. So if m1 is much smaller than m2, right? What happens if I what happens if I take out m2? So if I take out m2, okay, so if I take out m2, then this becomes m1 over m2 minus 1, and then this is u1, and then this is still m2 over here. Okay, and then if I take out m2, so I got m1 over m2 plus 1, right? The m2 will cancel everywhere, and then if m1 is much smaller than m2, okay, that means m1 divided by m2 is much smaller than 1, so it's approximately 0. Okay, so that means if I use this calculation, this term is approximately 0, and then this term is approximately 0. So what you get is that my final v1 is approximately negative u1. 0 plus 1 is divided by 1, and then u2 is already 0 from the beginning. So v1 is approximately negative of the initial velocity. Okay, so the tennis ball, if you hit something very heavy, it bounces back at the same speed but opposite direction. Okay, how about heavy mass? Heavy mass after collision. So for heavy mass after collision, what do we get? Well, v2 is using the formula that we just derived, m2 m1 u2 and then 2 m1 u1. Okay, and then this is m1 plus m2. So again, I will try to pull out a factor of m2 right? So it becomes 1 minus this over this u2, but this time is 0 actually. And then if I purposely take out a 2, then I got 2 m1 over m2 u1, and this pull out the factor of m2, so I got this over this plus 1, right? So that I can cancel the m2 everywhere. Okay, now because this is much smaller than m2, m1 over m2 is a very tiny number. So if this is a very tiny number, this stuff will become 0, and this is also 0 anyway, right? And this one will also become 0. So what we get is v2 is approximately still equals to 0 after collision. So the bigger mass discrepancy that we have, the closer this approximation is, right? So until it's a very tiny number. Okay, so if you throw a tennis ball against something very huge, right, the tennis ball will bounce back at the negative velocity of the initial, but the huge mass will still be at rest, will remain the same. So this is where we get our conservation of, this is true because we have conservation of momentum and conservation of kinetic energy. Okay, does anyone have any question? Is everything clear so far? Okay, so we covered a lot of ground today. We covered a lot of ground today. So we have learned potential energy, the graph, non-conservative force, and linear momentum. Okay, so hopefully everything is clear for everyone. So good, thanks, Eric. So I think that there's plenty of stuff that we cover for today already. So we should end the class soon. One last time, I will remind everyone that a few things that is coming up soon. So on week 6, next week, Wednesday, I will upload quiz 1. So you have practiced how to upload quizzes already, right? So solve the answer in a PDF file, upload to the Moodle. Okay, so next Wednesday, we will have quiz 1, and 2 weeks after that is our plan for the midterm test. So we will have our midterm test soon. Okay, small mass after collision is negative of initial velocity. Yes, yeah, that is what we so this is what we got here. So small mass velocity is negative of the initial small mass velocity. Okay, and then so secondly is I'm talking about black holes on Friday, but this is for the public talk lah. It's for outsiders as well as you guys if you want to join, but it's not compulsory. It's not related to the lecture course. On Microsoft Teams. So I can so I will put the link on the somewhere Moodle later if you want. Other than that, that's all for today. So can I explain why M2 on another Teams, on another page? So I will share the link later, right? So it's on another page. Why M2 is approximately equals 0? Because U2 is already 0. Wait U2 is already 0. Yeah, it's from the beginning. So nothing there. Okay. Any other question? Okay, so I will put the link to the talk later. It's on another Teams page. I created a new Teams page just for the talk because other people will join in. So if I put it on this page, right, then all the public outside people will come and see our chat and everything. So that's very weird. Then it's on a different page. Okay, so if there's no other question, that's all for today. I shall stop the recording. Stop recording here.